Okay, for people who are joining this live stream, we are talking about design of chemistry functionality in Wolfram language, and we are talking about template reaction and reaction apply, a representation of chemical reactions. And where did we get to last time?
Well, so we got stuck on the how you label the atoms on the left and the right side of the reaction.
Okay.
And so we've come back with a couple of alternative methods for labeling them. So you have in the reaction smarts that you see there. Okay, you might need to open this up in the prototype build if you want to run these things. I should have brought that up beforehand.
But in smarts, the atoms are given numbers. Do the numbers have to be consecutive, or could I put
any? They do not.
Okay, which so makes it really 12 or something in there if I wanted to.
Yes. Which can make it confusing because in general Wolfram language molecule, you refer to the atoms by their index, by their number. And so having two different numbering
does smarts allow one to do as the designator of the molecules? Do they have to be numbers, or could they be anything I want?
Let's see, for the mapping number, or
in the smart string, could I call that A or something there?
Oh no.
So it has to be a number.
Right.
At least in their version of smarts.
Yeah.
Okay. And in this formatting, the fact that it says O:3. And by the way, did you talk to the design group about these blobs here?
No.
As we discussed. Okay, so you will do that.
Absolutely.
Okay.
And I mean, once we decide on an alternate scheme besides colon number, then the plots will change accordingly. And if we have these this hover effect, then possibly you don't need the visual cue there, because if it's not something as simple as a number, then it could get unwieldy to put them all there.
Let's cross that bridge in a moment. Okay. Okay, and as I said last time, we should also talk about using this kind of hovering thing on ordinary patterns. Right? Did somebody take that? That will be for the user assistance crew. Did somebody take that?
Not that I know of.
Oh, come on.
I can try to join.
Who's project managing here? Is it
Addison? We didn't have one last time, so we have Kristen here now. So we'll get that to user assistance.
Okay. Okay. All right. So okay.
So the two alternates.
Yeah, I see it. I see it.
Okay.
But now the use of the pattern on the right-hand side here, I don't even understand this. So we have a pattern on the left and a pattern on the right. And in this case, the pattern on the right does not repeat the type of atom. Correct? More like our ordinary pattern variables. But now, if we were to reverse this reaction, we would need to know how to redo the bound variable stuff.
Right. In general, these things aren't necessarily reversible because you can write much more different kinds of patterns on the left and the right-hand side of the
In what way?
It's not one-to-one. It's not one-to-one, Stephen. It's one-to-many.
I just want to say, like, the patterns on the left can be vague. They could be a carbon or a nitrogen or something. But on the right, I don't know if it's there yet, but it should.
Yeah, I get it. I understand. So it's going to pick up whatever it was on the left, going to a definite thing on the right. And so this would be, how does smarts deal with the fact that there could be multiple things on the left, and then when it refers to it on the right, does it have to repeat that alternative from the left on the right?
If you put an asterisk, or in Wolfram language, if you put an underscore, that is the same thing as like inherited, and so we would use inherited when possible, or parse it.
Okay, so that's the case that So, I mean, what we need is a name, and that, it is superfluous. There's never a point. Okay, question. If the left-hand side contains carbon, nitrogen, or oxygen, right? And the right-hand side, no, I mean, what am I talking about? This is not a formal thing. This is a thing which actual atoms. So whatever was on the left better be on the right. Alchemists be damned. You can't transmute it, right?
I thought you can in smarts.
Well, I mean,
smarts you can, but we don't have to do that.
In a lab, you definitely can't transmute. But if we're talking about like an function that operates on like molecule objects and transforms them, you could write it to where it changes a carbon into an agent.
Okay, but wait a second. If I say this, that's just going to be garbage. And would anybody want to do that? Is there a good reason to want to do that, other than that you're about to make a mistake?
Let's see. I don't know that I would, but I imagine the users will.
Why? Why would they do that? There's no possible reaction that this could represent, right? It's either, if it's carbon on the left, it cannot be nitrogen on the right.
Let's see. So if you're trying, the template reaction can be used to model one specific reaction, but it can also be used to perform arbitrary transformations on a molecule object. Or almost.
Oh,
arbitrary.
I see. So that's a completely different thing. So that is then transmuting. That is a true graph rewriting in which you are potentially replacing the carbon-based life form with the silicon-based life form kind of thing. Is that the idea?
Yeah. I mean, and so
no, let's be specific. Let's be
so
specific. So this isn't a reaction. This is a pattern. If that's what you're saying, this is a chemical rule basically that says blah 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 goes to blah blah blah.
Yes.
Right? Okay, which is not the same as a chemical reaction. A chemical reaction cannot transmute carbon to nitrogen. But a chemical rule in which you're making a substitution in a molecule absolutely could. But don't we already have molecule, what was it called? Molecule
modify.
Has replaced substructure, which can do a lot, but essentially to a certain extent, you need to have callbacks. Like if you want to replace a substructure and insert atoms in the middle of it and rearrange the bonding, then it can only go so far.
Well, I don't know. What I would do is just turn the whole thing into a graph and do whatever graph operations I can on it and then take it back.
But graph doesn't support annotations sufficiently.
Well, no, hold on, stop. No, I mean, under the hood, we do have it as a graph, and we make.
Well, what aspects of graph don't support enough annotations? For stereochemistry or something, or what?
Well, no, it's more
even the atoms, they get lost.
Well, it's that you can't do like let's see, substructure.
Okay, have you reported that as a bug? Should we see if we can get Charles in this meeting, please?
Not at the moment. I mean, we have asked them about including
let's
annotations.
See if we can get. Could somebody please try and get Charles in this meeting?
Yeah. Yep. I can get him.
It's named template reaction because we have chemical reaction. For chemical reactions, everything specified, and here we are a little bit looser with stuff.
No, you're missing the point. If you're telling me that you can replace carbon by silicon, it is not a frigging chemical reaction.
Okay, let's ignore that. Like that.
No,
part.
we're not ignoring that because you told me that was a thing you could expect to do with a smart string. Is it or is it not?
Absolutely, but it's not the important ones. I don't think.
Okay, but we don't want to make that mistake. Right now, we're pandering to the smarts format. Okay, which it's a nice, convenient format, but whether we want to pander to that extent, I don't know. Okay, so my point here is what we're doing a transformation between molecules, or is it a representation of a physically realizable chemical reaction?
The first.
It's an arbitrary transformation between molecules.
Right. So people, like chemists, write these reactions. I've found a few collections in the wild, and I mean, in general, they might oftentimes be trying to represent something that is synthesizable. Like if you start with this starting material, we know.
Okay, so should I go get? I have a copy of this book called Name Reactions.
Oh no, no,
I go get it, and that's going to have real reactions in it, isn't it?
Sure, but I don't want to get too far here. I mean, I just want to say that like you'll have a series of reactions that happen step after step after step, and you don't want to write a computer like a function that simulates every step of that. You just want to skip to the end. You want to get, what could I produce if I have these molecules as starting materials?
Okay.
And so
what does that have to do with this? Yeah, go ahead.
That in that way, you would write a template reaction that pulled oxygen atoms out of the ether, that they just appear on the right-hand side, because you know that in these steps they could come. Like
okay, I get it. Okay, that's useful. Okay, and likewise, something from the left could just disappear because it goes into the the solvent, or just sort of floats away.
Exactly.
True. Okay. So you're representing, ignore the carbon dioxide that you're producing or something. Is that right? Yes. People would, yeah, okay. So it really isn't a reaction. It's a transformation. I mean, it's more like a chemical transformation of some kind.
Right. I mean,
it's really not a reaction.
Well, so I tend to think of it as related to reaction, because with the template reaction, if you gave it then a list of molecules, it would spit back a list of products, the reaction applied.
And sure, so would chemical transformation. It's not a reaction. Look, you're basically telling me this thing is not a physically realizable reaction necessarily. It is merely a representation of a transformation from one chemical to others.
That's fair.
Yeah.
Okay. So let's now discuss, in that chemical transformation, we have named pieces of the left-hand side molecule. And in principle, smarts notwithstanding, we could name a whole, what do we call them? What do you call them? Radical. What are they called? Chunk of molecule. What are those things called? The R's.
Radicals.
Functional groups, yes.
Okay. All right. You could, I don't know whether smarts supports it, but there's no reason you couldn't name, just like if I look at the name reaction book, okay, it commonly has an R in the sort of formula that gives for a reaction. Is that right?
Mm-hmm.
Yes. Yep.
Okay.
Yes.
But smarts is or is not supporting that.
You can do that, right, Jason?
Asterisk, right? I mean, so an R just means anything. And
no. It doesn't mean a single atom. But it does a star.
Right, so like in Wolfram language, an atom with an underscore.
No. That's not a. That is a single atom, a carbon, a nitrogen, whatever else. An R, as I understand it, in like the name reaction book, means any random functional groupy thing hanging off the end that could be 6 atoms in size. So what I'm asking is, in smarts, can you represent a 6-atom functional group somewhere as a pattern variable?
In principle.
Yeah. Generally in smarts, though, you don't worry about those radicals. They just get carried along based on how they were attached to the atoms that are specified.
Okay, let's be specific. Let me look up, give me a J random name reaction with
It's all the reaction. So.
Like the one we're seeing right now. That's
okay. Here we go. I've got a random one. I just looked it up on a random website. Okay, here it is. Okay. These are all your personal friends. I understand these reactions. I don't know what. Okay, so here's an example. So here we've got R prime, R double prime. Okay, and very bizarrely, we have multiple copies of R on the right-hand side.
Yeah, because there are 2 of those.
I see.
Two instances of those to make that bigger thing.
Okay, which is even more confusing. Okay, go ahead. Okay, so that now we would like to have a representation of this kind of thing, right? Which is challenging, even in that two is really puts a wrench in the whole thing. Okay, so but what I'm trying to understand is the pattern variables that we want should be able to represent things like these R's in here. How do we represent that right now? So if I say molecule, and you know, I've got my bonds and so on. If I have that, well, right now we're numbering. The bond is based on the number of that thing. But what I'm going to want to do is I'm going to want to have not an atom, but this radical there instead. Am I not?
But molecule, we do a validation if it's a valid molecule or not, which R you cannot do.
Okay, Bjorn, we're trying to solve this problem. I understand. With a molecule.
I put the name chemical reaction alpha. We have these things in alpha. We have name chemical reaction in alphas.
I think this misses Stephen's point.
Okay.
Bob, correct me if I'm wrong, but if we write the smarts for this one, we just need to represent the two separate instances of the carbonyl and make sure there's oxygen hanging out, right? If we're writing the smarts for this.
I don't know.
I have to reconnect. My internet is being unstable. I'm hearing everybody come in and out. I'll be back in a second.
We'll see you back in a moment. Okay, but you got the point that the natural way to do this would be to have a molecule in which, instead of an atom, we have some representation of this R thing. Am I correct?
It is not obvious that this is still a molecule. This is a little bit like chemical reaction and template reaction. Like this is, in my opinion, they're no longer a molecule. It's a molecule class or something like that.
Like a molecule family.
Yeah.
With everything that you can substitute for R prime and R double prime.
It represents a whole family, but in a general sense, it's just a pattern, right?
Yeah.
Right. So I don't understand. I mean, so that is R prime. I mean, they might represent functional groups or whatnot, but in the graph that is that molecule pattern, they're just an atom.
How do we? What are molecule patterns right now? What can we put in the molecule?
So you could use an R.
Where?
Let's in place of S. You should be able to type R there.
So in this molecule, in this thing here, I do that. And I would get this. Okay, so now let's say I put an R. I put a fish here instead. Okay, what happens if I put an R there instead? Oh my gosh.
Yeah, R is a special thing.
So R is a special tag for molecule pattern. What about if I put an R prime here? Like they did in that example. Let's go, oh, wow. Wow. If I say R, hello. Oh, wow. What the heck is it doing here? Can somebody explain? And where exactly in its documentation does it say anything about any weird behavior like this?
You're going in and out on me. What weird behavior are you seeing here? I mean, no, I wouldn't expect.
Why don't you reconnect it? Can you reconnect, or can you call in at least on audio on a cell phone or something? Okay, so something is very wrong here. Look. Okay, molecule pattern does not document anything special that it does, and I don't know exactly what the hell is prop arrow value doing here with that being in that font? What's going on here?
Yeah, this font is full.
That should be fixed.
Okay, but even so, what's happening? What is R?
R is
why
just
is it being treated specially?
It's the same as asterisk. It just means
anything. But why is it being treated specially? And the documentation for molecule pattern doesn't say anything about that. I don't understand why this is a pattern anymore. Okay, so it's a pattern in the sense that it has alternatives, but beyond that, this does not define how this manages to be a pattern. But in fact, you're telling me that R, mysteriously, the letter R, is a represents a wildcard atom. or wildcard functional group or whatever, right? That's what you're telling me, which is not documented anywhere here.
Yes.
So in a molecule pattern, you can have a wildcard functional group, which you cannot have in a molecule itself. All you want to be able to do but in a molecule itself, you want to be able to label atoms. But in a molecule pattern, you want to be able to have a random functional group hanging off it. Is that correct? Am I correct or not? What's
Let's see. So you can put an R inside a molecule, and it'll just be an R. It'll just display as an R.
Okay, look. What's the difference between molecule and molecule pattern?
Let's see. So in a molecule pattern, you could specify an atom as being carbon or nitrogen.
Okay, you've got alternatives. I said that already.
Okay.
In addition to alternatives, do you have wildcards?
Yes.
Okay, but you don't have it. You just told me you can put an R into molecule as well. So what's the difference between an R in molecule and an R in molecule pattern?
I don't know. I mean, I don't.
Well, who wrote?
Does there need to be one? I don't.
Who wrote this? I mean, you're telling me
I wrote it. So does there need to be a difference?
Okay, look. Molecule pattern. The question is,
I'm sorry.
If you're making, look. First of all, is it the case that in molecule pattern that you match an arbitrary functional group with an R when you use a replace with a molecule pattern? Does R match an arbitrary functional group?
No, I don't.
What does it match?
Let's see. R is in there just for convenience because users are going to type it. I've never put all that much thought into it.
But you made it represented. You represent it as a star here.
Yes.
But it doesn't mean a wild card, even though it's represented as a star.
Wait, how do you know it doesn't mean a wild card?
Because you just told me it didn't mean a wild card. You told me it doesn't mean something where if I say, does this pattern, molecule pattern match? Look, if I want to know whether some random thing with some random, functional group hanging off here matches this pattern, can I find that with molecule pattern?
Yes. So you could, let's see, you would do molecule contains Q of some molecule with a molecule pattern containing R's, and it would say either yes or no.
Yeah, but so R is a wild card. R represents any functional group, correct?
Yes.
Okay, so it is a wild card. But in molecule, it is not a wild card. If I did the same thing, molecule contains Q, and then I put, instead of a molecule pattern, I put a molecule there, it would fail. It says there's not specifically an R there, so I will not match it. Is that correct?
That seems reasonable. I'm not certain.
Well, you're not certain that's what it does.
Right.
Okay, fine. But this is what we're trying to clean up right now. Okay, so what we clearly need. So in a molecule, and like in a graph, we're going to need a notion of pattern variables for a molecule, for a graph. Okay, and what type of pattern variables do we have? Well, let me save this before we lose it completely. Oh gosh, where do I have the chemical structure? I don't know. Okay, so what we've got for a graph for a molecule, we have the possibility that individual nodes, so types of patterns, right? One thing is individual nodes are substitutable, right? Does that make sense? So that's the case of carbon or nitrogen or oxygen, or it's the case of X colon
To a degree, they're substitutable as long as they have the same number of connections.
Valence.
It depends on what you want to do with it, too.
No. I'm trying to define. We're going to have okay. We're trying to define a pattern, a graph pattern. Okay, and one possibility. Oh, I'm so confused here.
I'm a little bit confused that like I believe where you are going, but then this ruins things like molecule Q and graph Q because they are absolute objects.
Okay, we'll worry about that in a minute. And maybe what we have is that molecule pattern is what we use for all of these cases. Okay.
Okay, so
you're trying to shoehorn the fact that you can have a molecule that happens to have labeled atoms. Okay, that does not affect its moleculeness. If you understand what I'm saying. Right. But as soon as you have carbon or nitrogen or oxygen, you blew up its moleculeness.
I would argue this way.
Yes, I agree.
You agree with that? Yeah. Okay.
Yeah.
That's what I think too. Right. Yeah. So there is a special case of labeling atoms where that is purely the human is labeling the atoms. It doesn't affect the physical moleculeness of the underlying object. And so we want a notation for that, but we also want a notation for the case where we're representing things like this. Okay, which I would have expected to be more like the molecule pattern story, probably, or to be able to put something as a courtesy into a molecule and have it puff itself out into a molecule pattern. That is, if there was I don't know what the right name for it is, but if there was and this is a bad idea, but as such, but let's imagine that you could type molecule of functional group, blah, 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 in there, and that then this would puff itself out to a molecule pattern. So that the fact that it you type it in as a molecule is merely a courtesy. Does that make sense?
Absolutely. Just to make sure I follow what's going on. So you build your molecule, and as soon as you have a functional group or an R floating around, boom, that immediately pops you over to a molecule pattern.
Yes, that's what I'm suggesting. I mean, that's just a minor convenience, but go ahead. What are you going to say?
Okay. As far as different kinds of atoms at a position go, when you're doing a crystal structure determination, depending on your resolution, you might not know if it's a nitrogen or an oxygen at a given location in the crystal. You've got electron density there, but you don't know exactly what it is. And a lot of times they report them as it's this or it's that, or metals, very common. You have a mixture of,
yeah, I get it.
Yeah.
I get it. I mean, on minerals and things I've seen.
Yes, in minerals. Yep. Could be cadmium. It could be nickel or whatever.
Great. So you're telling me that that's not a molecule. It's a molecule pattern, and that's fine. Right?
I was just bringing this up as an example of where most people, chemists, would think of it as a molecule, but there's some uncertainty about it. So how do we represent that? Calling it a pattern doesn't seem to be quite right.
Well, I don't know. I'm not sure that it's wrong to call it a pattern. I mean, I think that it's more complicated in some of these mineral things where you have these fractional, whatever the
fractional occupancy.
Yeah.
Right. Molecule is the wrong container for that.
Okay. So we'll put crystals aside for now.
Yes.
Okay. But I want to come back to this. Okay. So we've got various different cases. One case is we've got essentially graph rewriting. Okay, this thing here is a graph rewriting story that in this notation is absolutely appalling notation here. Right? Or, I mean, it can get away with it, I suppose, because, wow, this is really funky notation. Because that R is guaranteed to be the same because it's two copies of the same graph, basically.
Yes, that's correct.
Yes. Yep.
What a weird situation. All right, I'm going to pick up another name reaction here.
We've been using that notation for, I don't know, hundreds of years.
Nobody's at least 100.
Not hundreds.
100, about 100, okay. But nobody's complained until now.
Well, but no, this really gets, actually, when I was teaching, this came up, this really gets to the point that we do that by, this is a way of eliding all the other information that is not actively important to the bonds that are forming and breaking
Right.
in this particular reaction. It's a
stuff
way
this
of just
away.
eliding an enormous amount of information.
Right, you focus on the important parts here. That's what you do.
Yeah.
Okay, so explain this one to me. What's that R sub 3 doing?
There are 3 copies of it.
Right.
There are 3 copies of R prime on that silicon.
Because silicon has 4 things, needs to have 4 things attached to it. So 3 of that are three of that are prime, and then that big
Okay,
one.
but in our language, for example, this is very different from, you know, R colon blank blank blank. So which is it in this case? Are they all identical? Are there
Yes,
3 identical
yes.
things
They should
there?
be
3
they should be.
identical. That's what that means there.
So 3 of the same. 3 of the same.
Exactly,
thing
3 of the
silicon.
same thing.
But you
Trimethyl
could also have,
silane.
but you could also have this, could you not? Where there are 3 different things hanging off that.
Yes.
You could. Sometimes they make them with 2 of one kind of group and a third of a different,
Okay, fine.
depending on the type of protection you want to do or the type of reaction.
All right, I'm just picking up random name reactions here, just for the sake of having something to talk about.
Mm-hmm. Yeah, it's good to do this. I mean, we find out what the breadth of the weirdness is out there.
Right. Well, so this case is fairly straightforward. That's a single pattern variable.
Yep.
Yeah.
Let's see here. Yeah, here's another one. It looks like our friend Mr. Corey seems to have a bunch of reactions that
He will have a
won Nobel
million
Prizes
of
for
them.
that.
Yeah,
He won
that's
Nobel
the thing.
Prizes for those reactions.
The Nobel Prize will do that.
Yeah.
Yeah, but he seems to be a single radical kind of guy, from what I'm seeing.
He was crusty from what I heard. Yes.
Yeah.
He's still around. I think he's still around. I think he's still alive.
Yes. That's right.
I think
Still at
even-
Harvard.
Yeah, he's my academic grandfather, by the way.
Oh, okay. Maybe I should meet him before while he's still around. Okay, let's look at another case here.
The one you just had is probably not a good example because it's multiple ones, right? With a bracket, square bracket, which we have no representation yet.
What is that? What does that mean?
The square bracket,
Yeah, what does that mean?
usually multiple copies.
It's an intermediate that's not isolated.
Yeah.
Yeah.
So we don't have a
Non-isolatable.
presentation for that. So
But I don't understand. What do you? I don't understand what it means. It just means. What does it mean? It's still a molecule, right? It's got some.
Yeah.
random-
It is,
This
but
thing
but it's not
forms when
isolated.
you're-
What does
yeah,
isolated
This thing
mean?
forms when you're doing that reaction, that thing forms, but you don't bother isolating it because you quickly do the next step, which is the one with mercury to get the final product.
Okay, but do we care about? I mean, that's just an annotation of that graph that says we
Correct.
didn't isolate it. Okay, so in this
Yeah.
case here, absolutely freaking bizarrely,
Marcos,
one-
those are called Marcos structures, which are a different beast altogether.
what do you mean? What is this? So-
Marcos structures basically mean that R1 can be attached anywhere in that benzene ring. We don't really care where it's attached. It's attached somewhere.
It's used very often in patents. So you
Yes.
get to cover the universe.
Okay, so explain what it means. So there's a bunch of hydrogens hanging off that benzene ring,
Right.
and this is an alternative. This is going to substitute for one of those. Is that
For what-
right?
exactly. Exactly.
Mhm.
For any of the 4.
Right.
By 4, we mean the ones that weren't otherwise attached to
No,
something.
well, there are 4.
Yes.
There are 4 hydrogens on that ring that are available to be.
No, I
substituted
get
by
it. I
that
get it. I guess
Yeah.
I'm just saying that okay. So okay, is that a specific thing relevant to hydrogens that you can lop them off and put these substitutions in, or is that could there be another case where you could lop off another? I mean, is that
No,
Yeah.
only
No.
hydrogens
Yeah.
are pawns
Marcos-
like that.
Yeah, Marcos structures tend to basically assume you can replace the hydrogen with any of a bunch of things. In this case, they are one.
Okay, let me pick another one here. This one looks totally horrifying.
You also notice here that they're using a pre-superscript or a post-superscript to differentiate the R's. In other places, people use primes.
Yeah, I see that. I mean, I see that.
And
I mean,
sometimes they use subscripts. It's a mess.
Right, which means we've got to basically allow them to use arbitrary names, in my opinion. And the fact that smarts only has a particular set of names is, well, that's the way that is. But okay, is this interesting, or is this just some weird thing with electrochemistry or something?
It's similar to the Diels-Alder that we were looking at last week, to be honest. But
okay,
a little more flexible because those A's are usually heteroatoms and not carbons.
Yeah,
pick up one more.
Charges there, right? So we don't have to representation with it as well.
Yeah.
I'm just seeing some here that look just like the other ones. A lot of other ones here that are just, well, that's a kind of a cool one. That looks just like, you see, I'm still, that's just like, this is a T channel, S channel. You like that, Ria?
Cycloaddition.
Cycloaddition and then decomposition, but in a different direction.
Yeah. What does the squiggly mean? What does that squiggly line mean?
Cis or trans.
Yeah.
It could be to the left or to the right.
Right. It doesn't matter for this case.
What does that mean? I mean, what when you say to the left or to the right?
Okay, you could draw to the left the way it is, or you could draw it to the right.
Yeah.
Alternatively, and those are different three-dimensional geometries.
So the double bond is not rotatable. So when you have the atoms on either side of a double bond, they stay there. They don't rotate around. So you can. So they behave differently depending on whether they're on the same side or
yeah, you can separate them. They have different melting points, different boiling points.
Right.
Okay. All right. So let's come back to what we're doing here. So what we've got is a variety of ways in which you can wildcard out pieces of a molecule, basically. That's what this is telling us, and that including this rather weird one here.
Yeah,
which you could take a subgraph. Well, it's all these things. It's not really a subgraph. All these things are things where you break a single bond and you can put something else on at the other end of it. Fair statement?
Mostly, some of them you create bonds where none existed before, like the
no, I'm just talking about the pattern. I'm talking about the representation of the pattern. I'm not talking about what happens in the reaction. I'm talking about what the pattern is, because in normal expression patterns, what we have is that a subgraph, a subtree, is a wildcard. You get what I'm saying? I mean, if I write something like so here, this is a form of pattern, graph pattern. Help me out here. I'm the thing that's confusing me. Okay, I know what's confusing me. Every single example we're seeing here, the wildcard piece, the pattern piece, the blank piece, is hanging off the end. That is, we don't see one of these R's that's in the middle. Do you get what I'm saying?
Not in these examples, but sometimes you do see that. For example, the ring might be variable size, could be 5, 6, 7, 8 membered ring. So you'll see N with around one vertex of the ring with an subscript, parentheses around the vertex with an N, meaning a variable number of
but I'm talking about graph rewriting. Traditional graph rewriting involves you take a subgraph of one graph somewhere in the middle of the graph and you rewrite it to some other subgraph.
Mm-hmm.
Yes.
Most of what we're seeing here is a very special case of that, where we have a thing hanging off the edge of the graph, and we don't have to worry about how this thing reconnects in, because it just has this one connection, and it's just going to that's the to change what's here. We're just putting we're putting a different thing there. We don't have to describe its other pieces of connection.
Right, and it has just one hair.
Yeah.
I'm trying to think of an example where we've got 2 or more hairs that get replaced, where the thing
would be
gets
in-
replaced.
That would be an EDTA ligand represented by
Yes.
an R group that has 2 or 3 bonds from the R.
Ah, yeah, that works.
Tell me what that is. Can I look that up? Or just send me a
Ethylene-
picture of the molecule.
Yeah, EDTA should
Enta.
probably get it by
Enta.
Googling.
Yes.
What is it? Ethylene diamine
Ethylene diamine
Diamine
tetracetic acid.
tetraacetic.
tetracetic acid.
Okay, well, I mean, with that, presumably we have that. If I say control EDTA, better have it. Yeah, there we go.
Yep.
And now we just say,
No, that's not it.
No, that's it. That's what.
It's another name for it?
For Doe. That's what Doe calls it anyway. Yeah, that's the
Yes,
structure.
that's it.
Yep, that's it.
okay, so now where's the what do we do with this creature?
So if you remove the hydrogens off of the oxygens, then all 6 oxygens can form bonds to a metal
Okay,
or other things. So here is a functional group that you could represent by R, and the R would potentially make up to 6 bonds to the other thing that it's bound to.
I see. Okay, so in other words, in one of these diagrams, there are multiple bonds coming out of the R.
There could
Correct.
be, yeah, especially for inorganic chemistry.
Yes.
Okay.
Often 2. But
So we have Charles here, I think, and you guys were saying, I was saying you take a molecule and worst cases you convert it to a graph and then you do computations on it. And you immediately said we can't do that because graph does not preserve annotations in the right
No,
place.
no, I immediately said the molecule is a graph. Like when we do computations on it, we are doing graph computations.
yeah, and I also said that graph itself, if I tried to build a molecule with a graph and put annotations on the vertices and the edges, as soon as I do something like graph disjoint union, I lose them all.
Okay,
So
so
I want to put 2 pieces together, 2 molecules together.
Charles, can you comment on that?
Right. So it's not yet implemented in short. So we did support of annotation or the inheritance, calculus of inheritance for unit variate operation. So, and we haven't yet done that for, NRE operations.
Okay, so you believe your calculus of annotations is complete for unary operations. Is that right? That it preserves correctly?
Yes.
Okay, so we can consider it essentially a bug that it is not correctly preserving annotations for NRE operations. Is that
Correct.
right?
Yes.
Okay, so, okay, fine. Well, hopefully that can get fixed, quickly, but it sounds like you have people with pitchforks clamoring for that to get fixed, Charles.
Okay. We'll make sure we have it in soon, I hope.
Any chance for 13.1?
No, with the timetable of snow, no.
Okay.
But well, we can look at, if there's some specific operation, we can probably, focus on those. But, going to the...
Bob, can you specify that? Which ones, or any of the rest of you specify that?
Which ones lose the annotations?
No, which ones do you really care about them? I mean, if Charles is going to make sure they don't lose the annotations, which ones do you really care about first? Not, if Charles is going to go fix these sequentially, which one should he fix first?
To do molecules, I would want vertex and I would annotations on vertices and annotations on edges.
No, we're asking about the operations, Bob. Which operations currently lose the annotations? Because what Charles claims is that unary graph operations do not lose annotations.
I would have to look and see. I do know that graph disjoint union does it because I ran into that a few weeks ago.
Okay, Charles is saying none of the non-unary operations preserve annotations.
Okay.
He's asking for a priority list of which NRE operations should he prioritize first in preserving the annotations.
I will supply him one by the end of today.
Okay, sounds good. Okay, but let's come back to this question about how we represent and we're over time, unfortunately, here. And we really need to solve this problem. I mean, I'm telling you, this is going to need a little bit of slightly heavier lifting than we're applying right now, because it's clear that there are a bunch of cases, and what is also clear is some of these look challenging. I mean, is there a smarts representation of this thing here?
Right, so I think it's a mistake to jump to the name reactions, because I looked through these, and a large percentage of them I think won't be representable as a template reaction object, or whatever we end up calling it. Like some of them you might need a whole function to represent that reaction, and it might involve several reaction chemical transformations, or whatever we want to call it. But the object I'm trying to present is a discrete operation. It does something, and it does that thing, but it doesn't do everything. It doesn't.
No, I know, but we need a representation of a molecular pattern, or whatever you're going to call it. Something which has, we've got these different cases. We've got the case with substitutions. We've got the case with functional groups, with arbitrary functional groups. Those are two known cases. And, we want something that can represent, we have lots of experience with having a pattern language for expressions. Okay, let's make use of that experience. The one thing we don't have good experience with yet is a pattern language for graphs.
Or any atomic object, right? I mean, once it's atomic, it's not open to the pattern matcher.
No, I understand that. But what I'm saying is we need a definition of pattern matching that works. Okay, we might have a definition of pattern matching that works for graphs. We're close, but we don't have that quite. Maybe Charles or Nick wants to say something about that. Charles, can you say something about what you've thought about in that regard?
Well, I can't go more precisely, but we are working on proposal and trying to write some prototype to see how the whole thing works. So still under development, okay, pretty much. So.
Okay, but I mean, in the physics project, we have lots of experience with graph rewriting. And however, the convenient form of graph rewriting is much more this hypergraph thing. But I have lots of code for graph rewriting from the 1990s that, in fact, we should look at again, because it uses pattern variables and so on to represent, to do the obvious kinds of things. Okay, but what you're trying to do here is you're trying to name. Okay, one type of transformation of graphs is one where you're merely trying to trace where the nodes go. And one of the confusing things is that we actually have two different. I mean, we have a perfectly good canonical representation of that carbon. Okay, independent of your one arrow carbon, that carbon is a certain atom number in our molecule representation, is it not? That's the thing that says bond 1, 2 means it's atom number 1 bonded to atom number 2, right?
Yes.
Yes.
Okay. So what's a little bit crazy weird here is that we're adding another layer. I mean, we could name this, this thing on the right-hand side has a perfectly good canonical name. We don't need the one arrow C. There's no new information here. Correct?
But it would be a double layered one, would be 3, 4.
What do you mean? So, I mean, in this case here, what we're saying is that,
like the carbon you just had, it would be not 1, it would be 1, 1, because it's from the first molecule pattern.
I mean, you're saying, right, you're saying that we have to label which, I see, so I understand. So you're saying atoms need to be labeled with which atom number they are in a given molecule.
Correct.
And which molecule they come
Exactly.
Right.
And I would love to get away from positional notation.
Well, I mean, so actually, to be honest, I was thinking about making it even more positional, like not, so right there, you have this 1 goes to C. So you're putting the mapping inside the patterns, the labels. You could also make the mapping itself an option to the template reaction. And there it would be list 1, 1 goes to 1, 1. And then what that means is the first atom from the first reactant becomes the first atom in the first product.
That's
and
I see it's convenient for computation. I find it for manual work very unhelpful.
Yeah,
I mean, there is
writing
no
these
version of writing these things in manually by hand that is convenient or nice. It's going to be like drawing it is the only way that I think that's going to make.
Well, I'm not convinced. I'm not convinced. We have a perfect. Look, in a situation like this, that's, I mean, we don't, that notation is perfectly reasonable. Whether it semantically makes sense, I don't know. But that notation for patterns, doesn't seem completely crazy to me.
Right. So I mean, as you like the farthest one down on the left, I mean, I could parse that and turn it into essentially internally something like the other forms we've seen.
Well, I mean, what's interesting about that is it would allow you in a molecule pattern, if you want to have a radical, I mean, then we could use the full pattern language. You just say, I mean, you could even do something like, this, and you could say, and you could have something where you, in other words, where that's how you would write, name it A, and it's a C, an N, or an O, or.
Right, and you could stick a condition on that, or you could stick a pattern test, right?
Yes, you could.
And that's the problem, because I'm not actually calling the pattern matcher.
Well, that's a technical implementation.
No, I don't know. The pattern matcher was written to handle like condition and pattern test and alternative and all those things, and everything that molecule pattern would cover. I need to write down values on verbatim blank.
Stop worrying about that. Okay, look, the right way to do that is all the simple cases you just handle directly. In some complicated case, perhaps what we do is we throw it at some future graph rewriting, full pattern language system. Okay? You're making, this protect because of implementation difficulty is the wrong thing. Right, let's not worry about the implementation. We can also say, oh, you can't put, it just doesn't work yet. Sorry, we don't support that yet. Get what I'm saying? But if it turns out it's the right thing conceptually, then this is where we should go. Now, in this case of A blank, that seems like that's a pretty good way to represent your star type R thing, right? And it also allows you to get the case that is, I think, rather important, which is the R blank versus R colon blank blank. Or just, in other words, you can say whether you need those things to be the same.
Yeah.
Oh, yeah.
One difficulty, one thing we have to be aware of is you could use a pattern within part of your atom specification, and you could, like you have here for A being C N or O, and on the right-hand side, you should only use that in one place, that A, and it should really mean the whole atom and everything else about it, and not just the atomic symbol part.
What other things might there be about it?
The formal charge, number of unpaired electrons.
How do you represent the formal charge? How do we represent formal charge?
It's an option of an atom.
I see. So instead of C, we say atom.
It would be C, comma, quote, formal charge, quote, goes to 1 or -1.
Is it quotes formal charge? Why is it quotes?
Because we don't have a defined symbol for it.
It's not a symbol.
Well, no, it's not an option.
Okay. Then what do you call that, Jason?
An annotation? I don't know.
Okay, fine. It's an annotation.
It's not an option because you don't have to call, you can't call set options on it.
Okay.
Right. And that's why it never made sense for me to call it an option.
Okay. My bad.
And we don't have a formal charge symbol in system.
Yeah. But there's formal charge, there's mass number,
Yeah. It's an
unpaired
isotope.
electron count,
Yes.
those sorts of things get
You
carried
can-
along. Some of them a reaction would change.
Okay, we still haven't solved this problem, and we're running into. I'm 13 minutes late.
The one thing I would be a little bit concerned, it's a variation of what Jason said. Like the condition on one is very sensible and probably implementable, but you can make the condition on the whole left-hand side, and then it becomes a nightmare. It'll never be solvable.
Fine.
Okay.
But I don't think. Look. Okay. To me, again, my initial reaction to this reaction stuff would be that this is a better approach than this. I think by the time we've got two different kinds of numbering running around, it just feels like we're just going to get everything totally confused. Now, the other point of view would be to say that nobody will ever type these things in like this. They'll type them in as smart strings, or they'll draw them or something like that. And therefore we should not obsess. We should put more emphasis on making these things be kind of formally clean and correct than we should on whether they're typable. Do you get what I'm saying?
Mm-hmm.
Okay.
And so I want to kind of understand, in the perfect formally correct version of this, what would you like to do? Because one of the things that's difficult here is if I take this molecule apart and put it back together again, all these numbers are going to be scrambled. Same thing I could say about a graph. A graph like this has, if I have the vertices and edges of a graph, I better keep those in sync or everything's going to be scrambled. Right? And that's what's happening here. These are the vertices and edges of essentially a graph.
Yep.
Sure.
And so my question is, Michael is saying it's very inelegant to have something that is sort of telling, referencing atoms by their positional, by their molecule number and position within the molecule. But my question would be,
No, I would not say inelegant. Actually, I would say it's reasonably elegant. But like my favorite example is like I have a grid and I want to make some rows green. And the fact that I cannot do this inline, that I have to, by the end in an option, dynamically count where I am, I find.
Yeah, it's horrifying. It's horrifying. And by the way, that's a thing that we should put in an ILD meeting to talk about that. But the point is here, annotatability, in-place annotatability is very nice when we can get it. Right. But clearly we've blown some of that up already by the fact that our atoms and our bonds are in separate lists that have to be kept in sync.
Yes.
Yeah, agreed.
So now the question is, if you want to annotate something, so you've got something annotated as a pattern, and might you want to annotate a bond with a name?
Yeah, because bond orders can change in a reaction.
Yeah. Or can disappear altogether.
Okay, so
no, but I don't think you would want to give it a name.
Why?
Well, so I could. All three of the examples that they just gave you wouldn't need that, right? So if you want to change the bond order, you just write a bond and you say which indices it is and you give it a new bond order. Or if you want a bond to disappear,
you give it a new bond order, as in you write it out in a different sequence in the right-hand side molecule.
In the products, yeah.
Okay.
Mm-hmm. And then if you want a bond to disappear, then it just
Make
isn't in the bond list. Yeah.
I would also think atoms and bonds are not at the same footing.
One would think so, right? Bonds are a much more ephemeral kind of creature. But okay. So the issue is you want to be able to label, but okay, here's the tricky thing. With this functional group thing, you are basically making a faux atom, a fake atom, are you not? This R is you're handling it like an atom, but it isn't really an atom.
Yeah. In some contexts, we call them dummy atoms.
Okay, fine.
Or it's sort of the around equivalent for an atom. There's an uncertainty of what it is.
Okay, that's even, yeah, but that's even more complicated concept because, I mean, to me, okay, but basically what you're saying is I can take a graph that represents a molecule, I can chop one of the atoms out, and I can replace it by some functional group that has the same bond configuration as that atom had. Is that right?
That would be lovely.
Yeah.
Yes. Yes. Especially for manipulating chemical structures to design new ones. I don't know if we would have a reaction that necessarily does that, but it's an operation that's very reasonable.
Okay, so in other words, an atom is removed. So it's like in a graph replacement setting. This is a case where the subgraph that you're operating on is a trivial subgraph. It's just a single vertex. And what you're doing is you're simply replacing, it's the most trivial kind of graph replacement. Now, currently, as I understand it, and Charles can maybe speak to this, vertex replace just replaces one vertex by another vertex, correct? It can't replace a vertex by a subgraph.
Yes, correct. Just the vertex.
Right. Okay. But the most trivial form of graph rewriting that doesn't have to address many of the kind of hair issues is we got a single vertex, you replace it with another vertex that has the same connections as that first vertex had. But you just reinsert something with that same collection of connections. Is that right? That's the chemically interesting case.
Yep.
Yes.
Okay. All right. So fine. So then what we need is something in molecule or molecule pattern that is basically going to be a potentially, in something like this. We might want a pure blank here, or we might want something that is more complicated. It might be a blank with the condition that its atomic radius is less than something or other. Or is that totally crazy?
Radius isn't really
Let's see.
the thing,
So
but
what
there are
you're
other criteria.
The size, it shouldn't be large, right?
So you can write A2 like atom, open close, formal charge goes to greater than 2.
Yeah. If you're looking for an atom like that.
Right.
Yeah.
Formal charge goes, I see that it goes to greater than 2. Okay, the example I was giving was more extreme. I mean, I have to believe that in one of these friendly chelates or whatever they are, or what are they called?
Zeolites. Zeolites are like a basketball, whereas chelates
right. In
make the basketball.
Oh, okay. Okay, thank you. Okay, in a zeolite, I have to believe it's got a cage of a certain size, and so in principle, you could say, any atom that fits in that cage.
Yeah.
Right. And so you could imagine extending the current notation to have the rule atomic radius goes to less than blah or something.
Right. Or alternatively, in this other notation, I could just have a condition here that says, atomic radius of A2, blah, blah, blah. If that makes sense. Right? If I say here, A2 bracket, well, it's not quite A2, it's some entity value thing on A2 with a condition. But okay, that's irrelevant. I think the main point here is that what we want is a pattern variable. Let's see. Yeah, I mean, I don't understand why this isn't a good idea. But by the way, the other type of kind of, faux pattern is a string pattern, right? We've already done a bunch of these things, using pattern language constructs with slight extensions and removals to deal with strings. And what's happened with biosequences? Do they not use those things as well? They use string-like patterning.
Yeah.
Yes.
Internal in for some of the string related functions internally, you can apply regex, for example, on the string assumed by the sequence.
Okay, fine. Right, but it's okay.
But the sequences itself have their own letters to designate alternatives,
Yes,
so you don't need it in the sequence.
Right. So
Right.
you have to account those.
But what I'm saying is we're using the syntactic structure of the pattern matcher while having some special casing for base pair substitutions and things like this.
Yes.
Right? So we've already got a precedent for doing that. So I think we should continue that precedent for molecules, which strongly supports using something that is essentially pattern matcher syntax here. And then simply defining how far you can go with the pattern syntax within molecules.
Yeah.
And there may be plenty of things where people never ask the question and never care. And the fact that you can't have a weird, conditional, a double blank, for example, you might actually want a double blank in your extensible ring scenario. You might want a double blank, if I'm not mistaken.
We might, yeah, but yeah, in this particular notation, that would be hard because it's both vertices and edges, or atoms and bonds that would be in the sequence.
Good example. That's a good example of why you can't do that. Listen, I really need to go to a different meeting, and we need to continue this. We're making progress. We're not quite there yet. If you guys have a chance to talk about it separately, my suggestion is think how we can leverage pattern matcher semantics as much as possible. Jason, don't worry too much about the fact that corner cases are unimplementable. Okay, well, I'm perfectly okay just giving an error message in those cases. Does that make sense? Jason is either lost his internet or he's freaked out. Okay.
Letter.
Okay, I have to run, but let's try to continue this soon, please, because I know we need to get this nailed down very quickly.
Yep.
Thank you.
Okay.
Thanks.